So here's just a quick extension, as I'd mentioned in class, just about L'Hopital's rule. And this is a BC extension, and so this is the sketch pad that I had up. Like so, if we were interested in here the limit again as x was approaching 3 for this f of x over g of x. Like as it sits, I can't get an answer for it. Like I would have to first recognize that there is a common factor, right? Here's f of x, the parabola. So x minus 3, x plus 1. So the x minus 3 is in common. Okay, and so that was really a theme with those, right? That if there was a hole in the graph there, if you're getting that 0, 0, try to get that common factor. Try to factor it out. Get that to cancel and go on. So L'Hopital's rule, so I'm going to try to give a little bit more justification as to why we can take the derivative so that this answer for that limit is the same as this limit. So again, individually take the derivative of each piece. So here we go. So if we think about so there is this hole, I've already kind of mentioned this, and if you factor it out, you can see that x minus 3 factor. So here's what I want to do with that. I want to think about how that connects to finding the linearization of f and g at 3. Okay, remember this word is just saying find the equation of the tangent line, right? So I want to find the equation of the tangent line at 3 for both of these functions. So if you're kind of imagining it, it's this one, right? I drew that pretty badly. So this tangent line here. And then there's a tangent line. Well, if this is a line, then its tangent is the line. So let's do that. And so in general, the linearization should be the slope times this x minus 3. Now, why is there nothing else there? Notice that both of those functions have a value of 0. So there is no like plus L of, or the function of 0, f of 0, or g of 0, because they're 0. Now, that is actually key because L'Hopital's rule wouldn't be applying if those weren't 0, right? Because remember, we're dividing these two functions, and if that's 0 and if that's 0, then L'Hopital's rule applies. So in order for L'Hopital's rule to apply, there shouldn't be, for this linearization, any other y-intercept other than 0. So take the derivative, evaluate it at 3, the answer is 4. Take the derivative, evaluate it at 3, the answer is 1. And so here's our linearizations. So the linearization is 4 times x minus 3. It's going through the same point, 3, 0, right? So again, I don't need to write it. And then here's the other linearization. Now, think about what linearization was all about. Like linearization was saying that as long as I don't move very far away from where I draw the tangent line, those functions should be approximate to their linearization. So it doesn't then take a big leap to think that, well, f of x over g of x should be about L1 of x over L2 of x. So the linearization for the parabola divided by the linearization for the line. Well, what's interesting though is that that is definitely true, because if I go back here and I think about, well, the linearization, so this tangent line here is obviously not the parabola. So as I stray to 3.5 or something like that, I'm getting different values here. But if I'm approaching the value of 3, now would that really be the case? So let's take this a little bit further though. Okay, So if I think about this linearization and think about like what we wrote with that, right? So it was this 4 times x minus 3. So it is f prime of x evaluated at 3. I should write that. So f prime of 3 times x minus 3, and then this one would be g prime of 3 times x minus 3. Now, in terms of like how far am I straying? Well, if I don't stray from 3 at all, shouldn't they be the same? Right? Like the linearization and the function agree at that moment. So yeah, they're different over here, but if I'm approaching the same value, and that's why in L'Hopital's rule we're going to see we're approaching the same value. Now look, isn't this really then the notion of that common factor? Isn't this the reason that as I take the limit as x approaches 3, do you see the 0 over 0 sitting right here? So just like we would end up factoring out something before and getting it to cancel, notice that what we've really done is turn this into that the answer is found for taking the derivative of those functions and then evaluating them at the same x value that we had before. So there is a little bit of extra on L'Hopital's rule. I hope that adds a little bit of justification as to why we're taking the derivatives of each piece. It's a nice tie-in to locally linear and linearization and things like that. So I hope that adds a little bit to your understanding of why we're doing that work. I'll talk to you later. See ya.